Good morning. This is the review for exam number 4. Let's talk about the equation for an isothermal change. Pressure times volume is a constant, right? Pressure times volume is a constant, and here is a problem for that. There is a bubble at the bottom of a lake, a tiny air bubble. Just tell me what will happen to the size of the bubble when it rises up to the top, assuming it doesn't break, What will happen to the size? It will expand. And the reason is because as it comes up, the pressure is decreasing. So I'm going to say that the radius of the bubble becomes double of what it was at the bottom. Okay? At the surface, it becomes double. Find the depth of the lake, assuming that the temperature remains constant. Because practically the temperature might change a little bit. So assume that the temperatures are constant and find the depth of the lake. So what's the information that I've given you again? The radius of the bubble doubles when it reaches the surface. That's all you need. Go ahead and try to do it. So if pressure times volume is a constant, okay, that's the question coming up. I just wanted to write it so people can think about what I'm saying. Let's take the bottom of the lake to be 0.1 and the top to be 0.2. So can't we say P1 V1 is equal to P2 V2? Can we say that? All right, that's what I'm going to do. There's the bottom of the lake. The pressure is P1, the volume is V1. At the top, the pressure is P2, the volume is V2. We know that P1 V1 is equal to P2 V2. Okay, wait. What's the pressure at the bottom of the lake? Is there atmospheric pressure at the bottom of the lake? Do we have atmospheric pressure at the bottom of the lake? The answer is yes, because fluids transmit pressure. So the atmospheric pressure is there. But over and above that, you also have the pressure due to the water column, which is given by H rho G, isn't it? So it's P naught plus H rho G. Yeah. So therefore, it's going to be P naught plus H rho G. What's P naught plus H rho G? P naught is the atmospheric pressure. H rho G is the pressure due to the water. So that's the total pressure there, isn't it? And what's the formula for volume of a sphere? 4 by 3 pi r cubed. So that's why you see that there. 4 by 3 pi r cubed, that's volume 1. Should be equal to, at the surface, what do you have? What's the pressure at the surface? Just the atmospheric pressure. That's why you have P naught, and then 4 by 3 pi. Then I say that the radius became double. So it's 2r raised to cube. So now you know that, will the r cubes get cancelled? Come on. Yes. And the 2 cube will become 8. 2 cube is 8. And therefore, when I solve it, I'm going to get P naught times 8 there. The r cubes are gone. And did you understand the next step? This is 8 P naught, and that's P naught. So bring that over to the other side. It's 8 minus 1, 7 P naught. So H rho G is 7 P naught. Therefore, substitute. And you know atmospheric pressure is 101325, isn't it? The density of water is 1000. G is 9.8. I did not have space there, so I calculated. I got the depth of the lake as 72.375 meter. Go ahead.
What is H?
H is the depth of the lake, the height of the water column.
Well, when you add the atmospheric pressure plus the HPG.
No, H rho G. Rho is the density.
Of the water, right?
Yes. Yes. Do you remember any equations for an adiabatic process? Right, correct? At least 2. Pressure times volume raised to gamma is a constant, and gamma is the ratio of specific heats, isn't it? And you need not cram the numbers, but can you tell me for a diatomic gas, how much is it? Diatomic gas, what's the value of gamma? 1.4. I told you, 1.67, 1.33, and 1.4. Okay, that was two years back. I know that's right. All right, the other equation is TV raised to gamma minus 1 is a constant. Those are the two equations. So here's the problem now. A gas at 27 degrees Celsius is adiabatically compressed to 1/3 of its initial volume. You have to find the, okay, I said at STP to make it easier for me to write. Find the final pressure and temperature. A gas at STP, so what's its initial temperature? 273 Kelvin. Okay. I don't like Celsius. 273 Kelvin. And what's the initial pressure? 101,325. Okay, so you have the initial temperature and the initial pressure. It's compressed to 1/3 of its initial volume. You got to find the final pressure and temperature. Okay, it's a straight application of those equations. Watch this. Is that right? P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Okay. And I'm telling you gamma is 1.4. So rearrange this to make P2 the subject because we're trying to find the final pressure. Would we get that? And then what is V1 by V2? How much is V1 by V2? It's compressed to 1/3 of its initial volume. 3, isn't it? If V1 is 3x, then V2 is x. So the ratio is 3. That's why you see this. The pressure is 101,325. The ratio is 3 by 1 raised to 1.4. You got to solve that, and you will get 471,722.26 pascals. Simple enough, isn't it? And how do you find the temperature? Same thing, but the other equation. Now use this equation because you have the initial temperature, 273. You have the ratio of the volume. So write the equation down, make T2 the subject. Again, V1 by V2 is 3. So it's going to be 3 raised to, of course, 273 times 3 raised to 0.4. Why? Because it's 1.4 minus 1, isn't it? Okay, when you do that, you get 423.7 Kelvin. Did the temperature rise, increase or decrease? Did you expect it to increase? Because you are compressing the gas. So you're doing work on the gas, isn't it? So if this question was backwards, like if I had said it adiabatically expands to 3 times its initial volume, then you would expect the temperature to decrease. And of course the pressure also to decrease. So it makes a lot of sense. If you compress a gas, its pressure increases, temperature increases, if it's adiabatic. Okay, so one time I asked a question like this, sometimes I can be very silly. I said, a gas is isothermally compressed to double its initial pressure. Find its volume and temperature. It's isothermally compressed, so what do you know about the temperature? Somewhere looking for a formula. The only formula you have for an isothermal process is pressure times volume is a constant. So when they tried to look for a formula with temperature in it, they did not find any. So you have to read the question. I said it's isothermally compressed. I gave the initial temperature. Many did not find the final. Okay. So that's Carnot's engine. So I'm going to combine three topics together. Not necessarily do a problem on it because it's so easy, it's just substitution. But I just want to compare the three. Carnot's engine, refrigerator, and a heat pump. You remember all those three? All right. First of all, what's the efficiency of Carnot's engine? How do you define it? What's the basic definition of efficiency?
1 minus.
Nah, I don't want a mathematical formula. What's the basic definition of efficiency? It's output divided by input. And the output is the work done. What's the input? The heat taken from the source, isn't it? So you got to know that formula first. You have to know how you get an equation. Simply writing an equation is of no use. This is what I was telling you. Efficiency is work over QH. QH is the heat absorbed from the hot source, right? What's work? What's the formula for work? In this case, otherwise you're going to tell me force times distance, I know. What's the formula for work in a Carnot's engine? See? What happens in a Carnot's engine? It takes heat from the source, converts a part of it into work, and rejects the remaining to the sink, isn't it? So if I tell you it takes 1,000 joules and rejects 300 joules, how much was the work done?
70%.
How much was the work done? 1,000 joules taken, 300 rejected. What's the work done? 700 joules. How did you get that? That's the formula for work. Work is QH minus QC. Did I make that clear now? Work is QH minus QC, so you get that formula. Because just now I told you work is QH minus QC, isn't it? And since the ratios of the heats and the temperatures are the same, the ratios are the same, now you can get the third formula in terms of the temperatures. But temperatures have got to be in Kelvin. What is the difference between a refrigerator and a Carnot's engine? What's the difference? What's the real difference?
It's not
Yeah, the refrigerator, you got to do some work, isn't it? And you're trying to transfer heat from the cold to the hot. Therefore, the formula changes. And it's not called efficiency anymore. It's called the coefficient of performance. And it's defined as? Did we use QC or QL? I can't remember. Okay, whatever it is. C stands for cold. You can have 1,000,000 equations written on that formula chart. If you do not know what each one stands for and how they affect the other one, it's of no use, I'm telling you. Then they'll all look like gibberish, like letters. Greek, what is that? Okay. And then, again, work is QH by QC. So, do you see the difference? And then in terms of temperature, similar. What about a heat pump? How do these formulas change? Does anybody remember that? COP? For a heat pump? No, actually the heat pump produces heat. You see, that's the difference. It's not transferring heat. Like the Carnot's engine and the refrigerator are transferring heat. Yeah, it's actually producing heat. So look at the difference. It becomes QH. It's producing heat by work. See, because the output is the heat. Are you with me? It's actually giving out heat. That's what we want it to.
So it's the direct opposite of Carnot's engine.
It is. It is. Why? Because the Carnot's engine is giving out work, taking in heat. What's the heat pump doing? Taking in work and giving out heat. Correct. That's why I keep saying physics is simple, if you understand. And nobody believes me. Or in terms of temperatures, TH by TH minus TC. Change in entropy. What's the formula for change in entropy? Change in entropy. Delta Q by, or dQ by, the average temperature. What does that mean? If heat enters a system, what happens to the entropy? Goes up or down? Heat comes into a system. Up. If heat leaves a system, its entropy goes. So if you mix a hot object with a cold one, the entropy of the hot one is going to go down, the entropy of the cold one is going to go up, but the net change in entropy of the system will always be up. You see that? We're going to prove that, and that's very important to do. But in such problems, it's actually two steps. First, you have to find the final temperature, don't you have to? When you mix the hot with the cold, so that's step number one. And then step number two, you find the change in entropy. Okay. So this is the problem here. Remember that it's T average. Can we have it in Celsius now? Can we have the average temperature in Celsius? No way. Because it's not a change in temperature. It's the temperature. It has to be in Kelvin. You put it in Celsius, you dig your grave in physics. Okay. So you have 200 grams of copper. It's at 80 degrees Celsius. That's the hot object. It's added to 500 grams of water, and this water is in an aluminum container of mass 100 grams. And both of them, of course, are at 20 degrees Celsius. That's the problem. So again, you have 200 grams of copper, which is at 80. You are just dropping it into 500 grams of water, which is contained in a 100-gram aluminum container, which is at 20 degrees Celsius. Now you go ahead of me. Can you find the final temperature? Copper has a specific heat, 385. 385 joule per kilogram per Kelvin. Do you remember the specific heat of water at least? 4185 or 4186, but take it as 4185. And that of aluminum is 900. Yes. 900. In calculations. All right. First, we have to find the final temperature. Here it is. Heat lost by copper. And the formula is, like somebody said, MCAT, isn't it? Mass times specific heat times change in temperature. Mass is, oh, you got to have it in kilograms, please. 0.2. 385 is the specific heat. Change in temperature is 80 minus dF. The important thing here is you always got to put the higher temperature first. Right? It's cooling, so it's going from 80 to TF. Therefore, it's 80 minus TF. When you do that, I just multiplied these two numbers first. I got 77, and then it's 80 minus TF. And then heat gained by aluminum and water. I'm trying to write both of them together, because I know the change in temperature will be the same for both. And what would that be? What would the change in temperature be? TF minus 20, correct. So I'm taking the mass of aluminum, multiplying it with the specific heat of aluminum plus mass of water with its specific heat, and then the whole thing is multiplied with TF minus 20. Now obviously I have to go to the next page, so this is going to be 90 and this is going to be half of this, so as we so when I did the calculation, just added those two numbers and set them equal to the heat lost. So heat lost is equal to heat gained. That was the heat lost.
It's 22.
22. You can do it your way, but this is what I did. So if you do it correctly, you get 22 degrees Celsius as the final temperature. How do we find the change in entropy? Change in entropy of copper is equal to delta Q by T average of copper. Hold on. What's the average temperature of copper, please? It started at 80, finished at 22, so the average is 51, isn't it? 51 degrees Celsius. And then you got to change it into Kelvin. And what is the heat lost? Wasn't the heat lost its mass times its specific heat times 80 minus 22? Come on, right? Okay, so I'm writing the average in a particular way, but that's what I told you before I wrote it. I'm just changing it into Kelvin right there, as you can see. And then I get 13.78 joule per Kelvin. That's the change in entropy of copper.
Mass-specific heat and change
In temperature. Yeah. Huh? 2? 21. 21. You know, many students have done that on the exams. They take the difference. No, the average is the sum of the two divided by 2. It was at 20, it went to 22. And the average is 21, isn't it? Okay, now this is the thing. What is the heat gained by water and aluminum? What's the heat gained by water and aluminum? Isn't it equal to the heat lost by copper? So you don't have to do all that again. If you could just find this, you know, in your calculator, find that. That's what I'm going to do. All right. So change in entropy of aluminum and water. See, I found that. You see that? Number in the numerator is 4466 joules. So I'm going to just take that. Divide by the average temperature is, of course, yeah, in 27 plus in Kelvin, I mean. So it should be, and you get 15.19 joule per Kelvin. But one of this is negative. Why? Lost. And this is positive. And therefore, when you take the net change, you got to keep that in mind. Simply don't go crazy and add them. Because one is negative, the other is positive. So the final answer is negative 1.41 joule per Kelvin. Maybe I stopped it. Yeah, it's positive. I had stopped it before the next line could come up. The change is always positive. 15.19 minus 13.78. There's one question which I did not think about when I was writing this in the morning. Would you be able to do this question in your head? Like, if I give you 10 grams of ice, 10 grams of ice at minus 10 degrees Celsius, okay? Can you find out how much heat is required to change this into steam at 100 degrees Celsius? Would you be able to do that? So you have 10 grams of steam at minus 10 degrees Celsius.
Minus 10 to 0.
Okay, so how many processes are there? First, you are heating ice, isn't it? Just to go from minus 10 to 0. So you need the specific heat of ice. You need the specific heat of ice. And all the constants are going to be given in the front, at least on the final exam. The front page, not with the problem. Okay, second process, ice melts. So what's the formula that you use there? Yeah, okay, mass times latent heat. Third process, ice has just finished melting, so you have water at 0 degrees Celsius. You got to heat it to 100. So that's MCAT again, MCAT. And then finally, you got to change the water into steam, which is mass times latent heat. Now be careful about the latent heats. In the first case, you're using the latent heat of ice. In the last case, you're using the latent heat of steam. Do you see that? Sometimes it's given as latent heat of fusion and latent heat of vaporization. So now some students, which one? Fusion means melting. Vaporization means vaporization. How do I explain that? Means liquid changing into? Because I've seen students mix up the two and then just lose 5 points. That's all. 5 out of 10 gone. Don't do that. I'll only blame you if you don't get a good grade in exam 4, I'm telling you. And that's on record. Next one is conduction. Conduction. Yes.
How did you find the average temperature?
Conduction. What's the formula for conduction? Yeah, you're waiting for it to appear on the screen.
Q over delta T.
Is equal to Ka.
Delta T over L.
Okay, what are the terms now? What's delta Q?
Change in heat.
Heat coming in or going out, right? And delta T? That delta T? Huh?
Time.
Time. Okay. K is called the sprinkle. Thermal conductivity. I know there are so many Ks. Thermal conductivity. And what's A? The area. Delta T, caps T, is the change in temperature or the difference in temperature. D is the distance between those two temperatures. So we're going to work out a problem which will have 3 steps. You have a brick wall 5 meters long, 2 meters wide, and 30 centimeters thick. And temperature on the outside, it's a hot day, temperature on the outside is 50 degrees Celsius and inside is 25. Find the quantity of heat conducted into the room in 1 minute. Heat conducted in a minute.
What's the K again?
K is 0.84 for brick. It's 0.84 watt per meter per Kelvin, but I said heat conducted in a minute. That's why you see this, because you have to have it in seconds, isn't it? And 1 minute is 60 seconds. So that's K. What's the area? 10. 5 times 2. 10 meters squared. And change is 50 minus 25 by 0.3, because you got to have it in meters.
Is this a big number? Oh, okay.
It is. It is a big number. So, is that what you got? Times 60, I think.
Yeah,
Is that times 60? Maybe I forgot. Or is that including 60?
4,200? Yeah.
I think that's including 60. 42,000 joules? Okay. So that's the first step. I don't like to ask you a problem like this. So if at all I ask you something like this, I would say, hey, what should be the minimum power of an AC? What should be the minimum power of an AC to maintain the temperature at 25 degrees Celsius? That would be the problem. So how much heat must the AC remove in a second? Oh, that's in a minute, isn't it? So divided by 60. 700 joules per second, isn't it? What's joule per second? That's the minimum power of the AC. Done. Whatever heat is coming in 1 second must be removed by the AC, right? So that's 42,000 divided by 60, which is 700. So 700 watts is the minimum power of the AC.
Isn't it only one wall?
Huh? Yeah, I'm just considering one. I know practically you never have one. You will have at least 4, including the roof if you want to. Come on now. But you brought up a good point.
What if you're on the second floor?
Just one wall?
No, all 6 walls.
Oh, you meant to increase it. I thought you were trying to say there's only one. Okay. Could be 6, depending on the question. But the problem here is, did you understand how to work it out? In that case, or all those cases, what changes is the area, isn't it? Nothing else changes. Come on. The area changes. Okay. So if there are 4 multiplied by the area. Or maybe the walls have different areas. Find each one and add them up. Or if they're made of different materials, well, then you got to individually find the quantity of heat conducted through each one and add them up. So that's the basic, because it's a review. Okay. So find the power of an AC, the minimum power of an AC. And the answer, we have already discussed that. Work over time. Okay. Then step 3. Step 3 of this problem is assuming that the AC is working for 10 hours in a day. What would be the total electricity bill in a month, just for the AC? If it's assuming that it's working for 10 hours in a day, how much would this guy have to pay in a month, just for the AC, at a rate of 10 cents per minute? 10 cents per unit, I mean. How do you do that? I mean,
All you do is 10 times 30 for the amount of days in a month, right?
yeah, because every day it's working 10 hours, and so 30 days, 300 hours. That part is correct, right?
You're 700 watts. 700 watts of power for just a minute, and then
That was for a second.
no, how much was that for? That was for a second, and then multiply. All you do is convert seconds all the way into.
We don't have to do that. But technically, you're right. In physics, you got to do that, but that makes the calculation tough. So what the electricity company does is, it charges us on a new unit. Just wanted to share this information with you. They use a unit of kilowatt hour. So we need not change the hours into seconds. You know what I mean? So that's...
You didn't make that specific.
That's why I brought this question up. What you were saying was right. If we had to do it the correct way, but it would be so tough, So, all right. Find the cost of using the AC. I believe I said 10 hours for 1 month at 10 hours per day. And somewhere I think I included. So the unit you have to get is kilowatt hour. So see how we get that. I'm trying to... That's... Okay. Would the unit be watt hour for that, right? When I multiply that? Okay, so 21,000. And how do you change that to kilowatts? Divide by? Take 3 zeros away. So that will be 210 kilowatt hour, which is 210 units, isn't it? And 1 unit assumed to be at 10 cents. We don't get it at 10 cents anymore, I think. Yeah, some companies give us at the 8.7, then they will charge us other things and make it up. You know what I mean? So it would cost that person $21 just to operate that AC. And it's not a very powerful AC, if you notice, because we were only talking about 1 wall. So we pay much more than this. And I don't know whether I told you this. If somebody wants to maintain the temperature at 20 degrees Celsius instead of 25, that person is going to pay much more than this. You understand? Right there, the calculations are upset, and so, yeah. Okay, so that's that topic. All right, the next one is radiation. Radiation. Does anybody remember the law, the formula? It's called Stefan's law. Be careful. Please study the laws of thermodynamics. One is on the exam. If at all you have any laws for the final exam, any laws that you have, just study those. I should be able to get Newton's second law from you. I mean, on the final exam, not for this. If I ask you what's Newton's second law, you don't know. Oh. So when you prepare for the final exam, please make sure you study. That's the only part and you can put it in your own words, you know. I don't care. You can put it in your own words, but you have to know what it is. Okay. Radiation, Stefan's law. Anybody? Delta Q by delta T is? There are so many terms coming up there. Sigma. Sigma is called Stefan's constant. Then you have the area coming in, isn't it? And it's what area was that? That's the surface area. And then you have a term called emissivity coming in. Okay. All those terms together. Heat radiated in a second. Oh, the problem was find it in a minute. That by an object. I thought I wrote the equation first. I didn't. Emissivity is 0.5. I tried to make it tougher. I said it's a filament. You know what a filament is? The incandescent light bulbs. Don't they have a tungsten filament inside, right? Okay. So suddenly I said, let me just add some more juice to this problem. So it's a filament. So if it's a filament, I have to give you the length of the filament, isn't it? You know, it's coiled in a light bulb. If you stretch it, it's going to be long. And I would give you the radius of the filament. Are you listening to me? Before we go there, can somebody tell me how to find the area of that filament? Be careful, think. I'll give you the length of the filament when it's stretched out, and I'll give you the radius, okay? How would you find? I asked this question on an exam.
You treat it as a cylinder?
Of course, you treat it as a cylinder. But what's the area of a cylinder? And so many did not know. Pi r squared times height will give you the volume. We're looking for surface area, right? What's the formula for surface area of a sphere? Of a cylinder. Thank you. It's just the circumference times the height. You should be able to figure that out. 2 pi r times the length. Okay. So the length is 25 centimeters. The radius is 1 millimeter. And its operating temperature is high, of course. It's 2000 Kelvin. And it's in a room or the surrounding which is at 300 Kelvin. So that's the question. You got to find the heat radiated in a minute. I've given you everything. All right. So just substitute into the formula. This is the formula. Delta Q by delta T, sigma A, e raised to T1 raised to 4 minus T2 or T naught raised to 4. Stefan's constant will be given to you. The area, like I mentioned, is 2 pi r times the length. You know that the millimeter should be changed into meter, isn't it? Okay, times the length must be in meters. And then Okay, so that's the surface area. And then the emissivity, and then 2000 raised to 4 minus 300 raised to 4. Let's check that out and see who will get the answer. Let's yeah, yeah. But was it 712 or 721? 712, okay. 712 times 60, and you know why I multiplied with 60, because I did say find in minute, and this was done for a second because I didn't have any number here. 42,720 joules. Which means if you have those old incandescent light bulbs, let's say 10 of these in summer in your home at night, each one is producing 42,720 joules in a minute, and the AC has to remove even that heat. Are you with me on what I said just now? It's not just the heat coming in from outside, it's also now the heat generated inside. And that's just from one bulb, light bulb. That's why, if there is a chance, please have all those light bulbs changed to compact fluorescent lamps. You know what I'm talking about, right? Those called CFLs. Now they last a long time, and they save you a lot of money. Because in the old incandescent light, for aesthetic purposes, yes, you need to have some of those. You know what I mean? But otherwise, change them. Because 95% of the energy, electrical energy, is converted into heat in those light bulbs. 95%. And 5% is converted into light. And yet they are called light bulbs. Now you can see why. Each one, every minute, is producing 42,720 joules. Yes.
What about halogen bulbs? How do they then?
Halogen bulbs,
They produce a lot of light, but
blinding to the eye. Have you noticed that?
I mean, yeah.
Yeah, it can't be, you know, not advisable at home.
I was just asking how efficient they were.
Oh, efficiency to, I could have thrown a number at you. I don't know the percentage.
yeah, but it's better than a common.
Oh, definitely. Yes, please. Root mean square velocity. One time I asked them this question as a 2-point question. Watch. I told them the velocities of the molecules are 1 meter per second, 2 meter per second, 3 meter per second, and 4 meter per second. Find the root mean square velocity. And they're looking for the equation. I can see them frantically looking for the equation. Those are my 2-point questions to see whether you really understood. How do you find the root mean square of this? Square each one, add them up, divide by 4, how many there are, and take the, that's it. Isn't the student expected to know that? Okay, 2 points. But there are 2 formulas for root mean square velocity. One is square root 3 RT by the mass, and the other is square root 3 P by the density. Let's look at those terms again. I would surely give you this constant, but if there is one constant that I wanted you to remember, it's this one. It's called the universal gas constant, isn't it? How much is it? 8.314. And T, again, it's got to be in Kelvin. What's M? Molecular mass in kilograms. Yes, in kilograms. Yeah, that's obviously one part where many of you go wrong. Please, in kilograms. I think I'm going to make you do a problem. I think it's oxygen, because that's the most important gas as far as I'm concerned. Find the root mean square velocity of oxygen at 27 degrees Celsius. Go ahead. Find the root mean square velocity of oxygen at 27 degrees Celsius.
To find molecular mass, do we multiply 16 times?
Yes, because it's O2. 16 times 2. 16 times 2, so that would be 32 grams. But 32 grams will not work. It should be 0.032 kilograms. 0.032 kilograms.
What I'll do is I'll divide that by Avogadro's number, then divide by 1,000. It still gives you.
There's no Avogadro number here. It's molecular mass. Okay, so you go. If you're using Avogadro number, then you're not using universal gas constant. You're using Boltzmann's constant.
At what
Okay, so you will get this, and the answer is 483.6 meter per second. Come on. Anybody got that?
Yes.
Okay. 483.6 meter per second. And you notice that it's really fast. Do you? It's fast. Right now, in this room, all these molecules are moving at great speeds. The lighter ones are moving faster. And obviously, we don't see it. That's why we don't go crazy. Just imagine you could see all those gas molecules moving. Okay. Shall we move on? Straight question?
You're getting credit from the physicists, though.
Expansion. Expansion. Formula change in length, isn't it? Change in length is original length times alpha times change in temperature. If it's change in volume, it's the original volume times beta times delta T. Does anybody remember the relation between beta and alpha?
3 times.
3 times, okay. So you got to be careful. That doesn't mean you got to always multiply with 3. If you are trying to find the change in volume, that's when you do. So here is a question. I want to see how you do this. You have water in a container. Its volume is, I think I changed it to 500 centimeter cube. I don't know. And the container is made of glass. Yes, it's 500, not 50. So water is filling a 500 centimeter cube volume container of glass, and it's heated from, both of them are heated from, yeah, it's 500, 25 to 75 degrees Celsius. Find how much of the water will overflow. Find how much of the water will overflow. Okay, situation, it's at 25 degrees Celsius, water is completely filling the container, right? So do we know the original volume of water? 500 centimeter cube. Now in this case you can keep it in centimeter cube because it's going to be a ratio. If you keep it in centimeter cube, you'll get the final answer in centimeter cube. So let's not change. Find that out. Find how much the volume of water will increase. What's the formula? Yeah, the only formula. Oh, you need the beta of water, right? Okay, alpha of glass. Wait, why should I even give you the alpha of glass? See, remember on the final exam, all the constants will be on the front page. Now, this is why. Because if I give you the alpha of glass, right there next to the problem, you are getting a clue. Glass also expands. That's why. Okay, so glass gets bigger. So what do you have to do? You got to find the actual increase in volume of water, then find the increase in volume of glass, and then do what? Add them? Subtract them. Okay. Alpha G, 3 times 10 to the negative 6. And beta for water is 210 times 10 to the negative 6. See, if it would have been so good if I'd given the constants as alpha and beta. I will not. Look, it'll be given this way. Cubical expansivity of water. And you're like, what is that? Cubical expanse. Aren't you expected to know? Cubical expansivity of water. Volume expansivity of water, right? So you know that. All constants are, it's going to be given as universal gas constant. And you're, what is that?
Would you say the relation between A and alpha and beta were?
3 times.
3 times between which one?
3 times alpha is equal to beta. But you don't have, okay, you have to do it for glass here. So to cut the pain out, I worked it out. Did I do it correctly? Is this right? I don't know. Is that right? For what? Original volume, beta of what? And I'm quite sure some of you are thinking about multiplying this with 3 now. Okay. It's the volume. I'm telling you all this because I've seen all this. That's why. Just remember a number 3. Oh, you got to multiply. Didn't he say it? Yeah, just multiply anything with 3 now. Yeah. So that's 50 because it's 75 minus 25 and you get that. All right. And then find the expansion for glass. 500 times 9. Now we know why it's 9. 3 times 3. At least one time I've seen people trying to struggle to multiply 3 times 10 to the negative 6 with, many times I've seen it written as 9 times 10 to the negative 18.
University?
College physics. University physics, yeah. When I see that, I'll laugh my head off. College physics, yeah. 9 times 10 to the negative 18. Okay, 0.225. I hope I'm doing the calculations correctly. Come on. Is there anybody checking? Yeah. So what overflows is... I thought I should not tell you this. You know, if this question had been changed to, the temperature changes from 75 to 25. And how much overflows? Or it should be not overflows. How much more water can be poured into it? You heard me, right? I'm cooling it.
Yeah.
The same thing, the same arrangement goes from 75 to 25. So I'm cooling it. So would I be able to add more water into it? Okay. Now, I'm sure you will get the same numbers, isn't it? But after you get the numbers, what do? You know, at least there's a problem in your head now, right? What happens to the glass? Does it become smaller? Yes. What happens to the water? It also becomes smaller. So how much more can you think?
4.8.
Huh? What do you do with these two numbers? Would you add or subtract or add? That's what. It'll be the same two numbers.
You still divide it?
I heard one person say it. The others, glass decreases in volume. Water also goes down. Why are you taking so much time?
It shouldn't change.
Will the answer be the same?
Yeah.
Why do I hear two weak answers? Like, yeah.
Well,
I know, you've been answering.
what
Look
I'd
at
like to say is,
look at all the other students.
in
Yeah.
ratio, they should be the same. Maybe not the same numbers.
Thomas is begging to disagree. Are you disagreeing with the answer? No? Will the answer still be the same?
It's proportional.
Are you talking about the difference should still be the same?
Yeah.
There's less water in there now.
I'm not saying the difference. Would you take the difference or would you add? That's my question. Pressure exerted by a gas. I did not get time to complete it. So can you just tell me the terms and what they stand for, and be careful. What's that? Oh, you're going to read? Okay. Mass of a molecule. Mass of a molecule. All right. What's this? Caps N. Total number of molecules. Total number of
Oh, if
molecules.
it's lowercase n, then it's moles. Is that what it is?
Huh?
If it's lowercase n, would that be just moles?
Yes.
Okay.
That's why I'm trying to use different symbols. And what is that? This is volume.
Then that's the
Volume.
average velocity.
And this is the root mean square velocity.
Well,
That's still not the same. One is the average, the other is root mean square. They are not the same. Let's fight.
okay.
So if I ask you a 2-point question giving all these terms, should be able to, right? Of course, I will not give you each one picked out, like, look, the total number of molecules is, no. You'll have to figure that out, and I'm sure you'll do it. I expect the whole class to do much better on exam 4. That's what's been happening. That's the trend. Okay, and then one word about the lab that we're going to do. I just attached it to the review because you also have simple harmonic motion, isn't it, on the exam? Don't you? Okay. We'll not have much time to talk about it, but this is the time period for a pendulum. L is the length of the pendulum, G is the acceleration due to gravity. And this is for what? A spring with a mass attached. This is the formula that you're going to use in today's lab, the second part. You see the second part? You are using the computer, you're going to find the time period. Now, what do you mean by time period? Time taken for one oscillation. So, on the computer screen, you're going to get waves. Have you all done the pre-lab? You should have read a little bit. Yeah. Okay, so you find the time for this, find the time for this, and take it for 7 peaks. If you take the difference between adjacent peaks, aren't you getting the time period? So you would get it like 6 times, and then take the average of that. So you have the time period, and this is supposed to be a perfect lab. So you have this. What's that? Mass. Mass that's hanging there. Please don't follow the procedure given. They say 200 grams, but use only 100 grams. Right? Because below this, you're going to have a motion sensor. And this would be the most important thing I'm telling you. Pull the spring down by 5 centimeters. Because if you pull it down anything more than that, that mass that's there will fall on the motion sensor and crack it. So it'll be oscillating only this much, but that's okay. That's when you will get a perfect waveform. Otherwise, if you pull it down too much, it'll go side to side. And so the motion sensor will not see it. You see that? And in between, when this goes off, the bottom of the mass goes off, it'll see the ceiling. So you will see your graph spike. That make any sense? So it goes off. And therefore, you have to adjust the motion sensor straight below that mass. And if you do all this, it takes 5 minutes. And I've seen groups struggle with spiking and all that. Yesterday I found a group. Why am I recording all this? Do is, once you get the time period, why did I do that? Once you get the time period, what's this again? Now there is a problem there. The spring that we are using in the lab is a heavy spring. Therefore, its mass is not negligible. You don't have to add the whole mass of the spring because the whole mass of the spring is not suspended. So you take 1/3 of the mass of the spring. Now we could prove that by integration. We don't have the time. So you would find the mass of the spring, take 1/3 of the mass of the spring, and add it to the 100 gram. That's clear, isn't it? So that's actually the mass that's oscillating. 1/3 of the mass of the spring plus the 100 gram. And you would find K. Again, I'm telling you, do not follow the procedure in the lab. I've changed it to where you found the time period, you know the mass, like I told you, and you find the K, spring constant. That's one method. Now the other one, what did I tell you? I'm just going to give you the spring, a meter stick, and 4 50-gram masses. You got to figure out another way of finding the spring constant without using the computer. Calculate both the K's, bring it to me. If they are close to each other, you're right. If they are not, you're wrong. So that is what you're going to do. Now, continuing into simple harmonic motion a little bit. Does anybody remember the formula for velocity? No, displacement. Displacement in simple harmonic motion. X is equal to A cos omega t plus or minus phi. What's A? Amplitude. What's omega? Omega is the angular frequency. Omega is 2 pi f. Because frequency is just the number of oscillations in a second, isn't it? And then you also know that f is 1 over the period. Does anybody know the formula for velocity? General formula. General formula. It's omega a squared minus x squared. And you know x is a variable, right? And when x is equal to a, it has minimum velocity, which is 0. When x is equal to 0, it has maximum. We know all that. I think so. And what's the formula for acceleration? That's d squared x by dt squared would give you minus omega squared x, isn't it? And then if you, no, I didn't want you to see that. That was the other method that I wanted you to find on your own. This is the method that you're using. You do this first. Didn't I already tell you about this? Okay, told you about this. I just wanted to write that d squared x by dt squared plus omega squared x is equal to 0. Didn't we get that? Right? And the last thing is omega is root Thanks, Mike. And formula for potential energy is 1/2 k x squared. There's nobody in this room. Okay, what's the formula for kinetic energy? 1/2 k a squared minus x squared. That's for kinetic. What's the formula for total energy? The sum of the two, and you would get 1/2 k a squared. So that's what you have for exam 4. Thank you. Wish you the very best on the exam.